afternoon from Cape Canaveral Space Force Station in Florida, where we await the maiden flight of Terran 1, the world's first 3D printed rocket. Today's flight is named Good Luck, Have Fun, or GLHF for short. This is Relativity's first ever launch. We'll be bringing you live coverage from Launch Complex 16, our launch pad at Cape Canaveral, as we prepare for historic liftoff. I am Rachelle Aniceto, the Chief of Staff for the Vehicle Architecture and Technology team at Relativity Space. I support our Chief Architect in the design, development, and product management of our medium to heavy lift reusable launch vehicle, Terran R.
And I'm Arwa Tazani Kelly, Technical Program Manager for Test and Launch at Relativity Space. I'm responsible for supporting the teams that design, build, and operate our test and launch sites across the country for both our Terran 1 and Terran R vehicles, including for operations on their stages, engines, and propulsion components. Together, we'll be guiding you through our first launch attempt today. Now, the purpose of Good Luck, Have Fun is to test Terran 1's capabilities. This is the first launch, meaning that while we're aiming for Terran 1 to reach orbit, our primary focus is on gathering the data and learnings necessary to develop Terran R, our much larger, medium to heavy lift reusable launch vehicle. The lessons learned from this mission will also enable us to improve our software-driven approach to manufacturing.
Today's launch includes many firsts. Terran 1 is the first 3D printed rocket, which is 85% 3D printed by mass, and is in a race to become the first Methalox-propelled rocket to achieve orbit. If orbit is achieved, Relativity will also become the first venture-backed space company to have successfully reached orbit on its first flight.
And it's worth noting that while Terran 1 will be capable of lifting 1,250 kilograms into low Earth orbit, or LEO, today's launch does not have a customer payload. We do, however, have a memento on board, one that's quite unique to Relativity that we'll tell you a little bit more about later.
Liftoff is currently scheduled approximately 56 minutes from now. This estimation may change as we work through our countdown. We'll keep you updated along the way. Today's launch window lasts for about 3 hours, giving us time to troubleshoot any issues. If any unforeseen issues arise during the countdown, we can pause the launch sequence if necessary. And with that, Arwa, what's the mission status update?
Well, as you said, we're at T-minus 55 minutes and counting. We just received confirmation that propellant load is wrapping up for both stages. The weather is trending in our favor. However, we're keeping an eye out for medium winds that are gusting at about 22 miles an hour. And there are a few scattered clouds, but conditions are currently within limits. So the range is green, the vehicle is healthy, and we're progressing well towards our scheduled launch time.
This is so exciting. We're getting closer and closer. So Arwa will provide regular status updates over the course of the countdown. In the top left of your screen, you can find our countdown clock to help follow along in our pre-launch operations.
And now, ahead of our terminal countdown, here are some other quick facts to bring you up to speed on Terran 1. This launch vehicle is a 2-stage expendable rocket. It stands at 110 feet tall and is 7.5 feet in diameter. As far as we know, this is the largest metal 3D printed object to exist, much less attempt orbital flight. It is 85% 3D printed by mass, and there are 9 Aeon 1 engines on the first stage and a single Aeon vacuum engine on the second stage. All Aeon engines are, of course, 3D printed. Terran 1 and Terran R are both Methalox rockets. This means that they use a combination of liquid natural gas, predominantly composed of liquid methane, and liquid oxygen, hence Methalox. This propellant combination is becoming the choice for next-generation reusable vehicles, including our next rocket, Terran R. We believe it will also be easiest to eventually transition to methane on Mars. The important thing here is that Terran 1 will give us parallel learning for Terran R. And we'll dive deeper into Terran 1 and share updates on Terran R development over the course of the webcast. But in the meantime, Rachelle, let's talk a little bit about who we are as a company.
We often get asked, what is Relativity Space? Well, we are a rocket company, and we put our customers first. We're building rockets to designed to offer high performance and reliability while costing less to build and fly. And if that wasn't enough, we have the long-term vision for expanding the possibilities for the human experience by creating humanity's industrial base on Mars.
And building large-scale metal 3D printers could make Relativity's mission possible, including early Martian settlements. We see 3D printing as an automation tool. It allows us to remove fixed tooling and really embrace software-driven manufacturing. Our first 3D printers were developed about 7 years ago, and since then, we've improved on speed, scale, and complexity across 4 generations of printers. We intentionally started with orbital rockets because we saw an incredible market opportunity in space, and we believe they're among the most complex proofs of concept to develop this advanced manufacturing technology. There's also a natural incentive cycle between 3D printing and rockets. The lighter weight a 3D printed product is, the faster it is to build, and thus the cheaper it is. The desire to make a rocket lightweight is really to ultimately increase our payload capacity. This also means we can optimize for cost, build and iteration time, total part count, and reduce fixed tooling. Our Stargate printers were used to manufacture our Terran 1 vehicle, and we're currently expanding into a 1 million square foot facility known as the Wormhole to allow us to continue the manufacturing of Terran R. This isn't only exciting for our internal teams, but it's also exciting for our customers.
Terran 1 and Terran R have already been met with significant market interest. To date, Relativity has publicly announced nearly a dozen signed customers for commercial and U.S. government payloads. Some customers include OneWeb, Iridium, NASA, and the Defense Innovation Unit. Currently, Relativity's customer contracts amount to more than $1.65 billion. Relativity is a private venture-backed company. To date, we have raised over $1.3 billion in capital with our most recent $650 million Series E round.
That's right. I do want to switch gears for a minute here. I think we'd be remiss not to take a moment to acknowledge that today is International Women's Day and to give a shout out to our hundreds of incredible female colleagues who are contributing to Relativity's mission. I am so proud to work alongside you all.
Good luck, have fun is the maiden launch of our 3D printed Terran 1 rocket. Terran 1 is an orbital class rocket, and of course, reaching orbit would be a total home run. But truly, we are looking for some important base hits here today. Notably, a key objective for today's flight is largely about proving our hypothesis that 3D printing is a viable way to manufacture a rocket, and that it can successfully withstand the pressures of flight. Through robust ground testing, we're confident that we have a real shot at proving just that. And the more data that we collect from this first flight means that we'll have access to more insights, giving us confidence that we're able to execute on Terran R and help us solve all the hard problems that come with building a medium to heavy lift reusable rocket. As a business, we're following a Pathfinder product development approach. The Terran 1 that you see on the pad today has always been our Pathfinder. It was designed to be a development platform for Terran R, and it has served us exceedingly well to date in that capacity as we progress through printing and testing ahead of today's launch. Arwa, maybe let's dive deeper into what we might call a success for today's launch.
Yeah, absolutely. Clearing the pad, Getting out over the ocean and passing the point of maximum dynamic pressure, or max Q, would be a big inflection point for today's launch. This is because it's the point where the structural loads on the vehicle are the highest, making it one of the most challenging phases of flight. This is the point in flight where we really want to prove much of what has already been proven on the ground. During acceptance testing, the vehicle withstood loads even beyond what we anticipate it will encounter during flight. So passing this milestone would effectively demonstrate that 3D printed rockets are structurally viable. If we make it even further to stage separation, we will have achieved a full first stage flight, and that'll be another big accomplishment from the team. From there, we'll attempt to light the second stage and get Terran 1 to orbit.
So at this point, I'll be honest, it'll take some restraint to keep us seated here. If the stages of flight were a video game, this is where I would start to feel like it's a bonus round unlock. And just as a reminder, since today is our first flight, for stage 2, we are targeting a 200 kilometer by 210 kilometer orbit, which is not a traditional orbital target. But that is our target today, given that this is our first launch and not a customer mission.
That's right, and we have strict safety protocols in effect for today's flight and are closely coordinating with the FAA and Space Launch Delta 45. These protocols are, of course, standard for all launches and ensure that no one would be in harm's way if there were to be an anomaly.
And as a reminder, there is no customer payload on this flight. Instead, to celebrate how far we've come, we've mounted our first ever metal 3D print from the first generation Stargate printer inside of Terran 1's nose cone. And while we're on the topic of setting expectations, we will also note that we are unsure how much of the second stage flight we will be able to share with you live. While we do have cameras on board, we will be prioritizing vehicle telemetry sensor data for this launch in order to maximize our learnings. And as a result, the video connection could be spotty. In the event that we do lose our video, we will do our best to keep you up to date as we receive telemetry. Now let's talk about the countdown overview.
Well, the window for today's launch attempt opens at 1300 Eastern Time and lasts for 3 hours. The pad was cleared of all personnel at T-4 hours, followed by the start of propellant loading. Propellant loading is now wrapping up, as I mentioned, and we're currently going to continue topping off our tanks and conditioning our propellant after that. At approximately T-20 to T-15 minutes, the launch director will poll the launch teams to ensure that all subsystems, weather, and the range are go for terminal count. Terminal count will then be at T-70 seconds, and it's when the vehicle's internal flight computer takes control of the countdown. Now, while we wait for T0, let's talk about the process that got us here. So again, Terran 1 is 85% 3D printed by mass. The items that are not 3D printed include rubber seals, computer chips, valves, and other similar items. Relativity sees 3D printing as an automation technology, and we believe that long-term 3D printing will rapidly democratize space. We've already been able to unlock rapid part count reduction and rapid design iteration, and we're still in the early days of what's achievable. Now, we use 2 classes of printers here, powder bed fusion, or PBF, and vertical wire arc additive manufacturing, or WAM.
PBF is a process that uses a heat source, such as a laser, to sinter or fuse powder particles together in a layer-by-layer process. What you see on the table in front of me are a few sample PBF printed parts. These are not flight parts, but just examples for us to see today what kind of parts we could print using this technology. For PBF, we use this technology to print our Aeon engines. These are the 9 Aeon 1 engines on the first stage and the single Aeon vacuum engine on the second stage. PBF has allowed us to increase our reliability through lowering our part count.
And on the other hand, our proprietary Stargate printers use WAM for printing the vehicle structure. The material we use is a proprietary metal alloy developed in-house. It begins in a wire spool, and that wire is then fed into a Stargate printer. It's then heated and cooled rapidly to form small beads that, in succession, create the vehicle structure layer by layer. That includes the Stage 1 and Stage 2 tanks that hold the propellant, their internal ribs, the common domes, and the nose cone. This is essentially what makes up the bulk of the visible part of the vehicle on the pad, except now it's painted white instead of the native silver that you see here. Now, I do want to mention that our Terran 1 was vertically printed using our 3rd generation printer, but our 4th generation printer will move horizontally to increase print sizes for our next vehicle, Terran R. But of course, the star of today's show is still Terran 1.
That's right. Let's do a deeper dive into Terran 1 and walk through the architecture shown on the screen. Terran 1, as mentioned before, is 110 feet tall and 7.5 feet in diameter. Starting from the left-hand side of the diagram and at the bottom of the vehicle are 9 Aeon 1 engines. As mentioned before, these are printed using powder bed fusion technology. Each Aeon 1 engine has a thrust capability of about 23,000 pounds at sea level. In total, this gives us a max total liftoff thrust of more than 200,000 pounds. The Aeon 1 engine is designed with a gas generator cycle, and each of these engines also has thrust vector control actuators, or TVCAs, to gimbal the engines during flight. We have completed more than 2,000 engine hot fires and 10,000 seconds of runtime across 191 Aeon 1 hot fire tests. The Aeon 1 engines are attached to the vehicle through the thrust structure. This is what takes the load from the thrust coming from the engines. And above the thrust structure is the stage WAM printed tanks that Arwa just spoke about. These hold the liquid oxygen propellant on the top tank and the liquid natural gas on the bottom tank. The tanks are actually pressurized using an autogenous pressurization system during flight. We run propellant through heat exchangers mounted on the engines, which convert liquid propellant into a gaseous state, and this is piped back into the top of the tanks to maintain the required tank pressures. Above stage 1 is the WAM printed interstage, which holds the stage separation mechanisms. For stage separation, we use pneumatically actuated pushers. Above the interstage is stage 2, which has a single Aeon vacuum engine. This engine has a thrust capability of more than 25,000 pounds in vacuum and has the capability of multiple restarts. Stage 2 also has WAM printed tanks just like stage 1. And above stage 2 is the WAM printed nose cone. For future missions, this would be replaced with a fairing and also have a fairing separation system. We have no customer payload for today's launch, since this is our first launch. The payload capacity of Terran 1 is 1,250 kilograms to low Earth orbit, or LEO, and 900 kilograms to sun synchronous orbit for our customer missions. All data from Terran 1 development will be fed into Terran R. But our Terran 1 rocket is only a part of the formula. We also have a historic launch location.
That's right. We are launching today from historic Launch Complex 16 at Cape Canaveral Space Force Station. Between 1959 and 1988, this site supported a total of 141 launches. It was initially built for the Titan missile launches, and it was transferred to NASA for Gemini crew processing and static test firing of the Apollo service module's propulsion engine. The Air Force then used it from 1972 to 1988 for the Pershing missile launches. After that, the site sat abandoned, and Relativity then got the right of entry in 2019. In 2020, we initiated land clearing and construction. We built the whole site from scratch, and in less than 2 years, the team cleared, demoed, and built the pad to what you see here today. This includes the pad deck, the transporter erector, all the commodities and utilities, the office space, and of course the integration hangar. We conducted multiple hot fire tests after that and are here today to launch. Good luck, have fun. This will be the site's first launch in over 35 years. Now let's take a minute to visit our facilities across the country. right, and a quick status update here. We are just over T-minus 36 minutes and counting. You may have seen a brief moment where the T-clock said hold, but that was just a graphical error. We are still go as of now. Weather violations are tracking none. The medium gust winds at 22 miles an hour are still within range. The clouds are still within the limits. The range is green, and everything is go for our scheduled launch time. Now, while we wait, let me take a minute to explain a little about what you're seeing on the pad. The rocket rolls out of the hangar horizontally and is then lifted vertically by the transporter erector. That is the black truss structure you see behind the rocket. The 4 large towers surrounding the pad make up our lightning protection system. They protect the vehicle from any direct lightning strikes. Inside of those, we have 4 small black posts around the pad called rainbirds. They're used for acoustic mitigation for the rocket and do so by covering the pad with water to dampen the reflected acoustics. The small flame that you see there at the bottom right of your screen is the flare stack. It burns off flammable gases from propellant loading, venting operations, and priming of the engine igniters. It's a little harder to see, but the small slide-looking structure beneath the vehicle, there it is our water-cooled flame diverter. It's used to mitigate the heat from lighting the engines, and it directs the exhaust plumes away from the vehicle. You'll also be able to see what looks to be 3 different levels under the rocket. The largest and lowest level is the pad deck, and directly above it is the launch table. This is where the launch mount pins to the pad and creates that flame duct. The launch mount on top of it is one component of the transporter erector. It transfers loads into the pad deck during hot fire tests and, of course, at engine ramp up at launch. It also contains the release system, or hold downs, and the quick disconnect or QD carriages that provide propellant and other commodities to the vehicle when it's on the ground. Now, I do just want to take a moment to thank and give a shout out to the ground crews out here for all of their hard work. They've helped us build and operate our launch infrastructure, and they support vehicle integration and testing at one of the most historic launch sites in the United States. As you can imagine, there's a lot of work that happens at the pad to properly prepare for launch, and their work includes the design, build, and installation of launch equipment, creating and implementing the relevant procedures, integrating the vehicle, troubleshooting it, and working with our engineering teams to ensure that we optimize the vehicle and operations every step of the way. Thank you all for your amazing work.
These teams have also supported our rigorous test campaigns. While this doesn't guarantee success, it certainly helps us, given we're attempting so many firsts. As a reminder, we're launching the first 3D printed rocket. We're racing to have the first Methalox rocket to reach orbit, and we're hoping to be the first venture-backed space company to have successfully reached orbit on its first flight. Now let's quickly recap what we've done to get this 3D printed rocket here today. And it all started through manufacturing at our Long Beach factory. This is where we print and build our rocket. We build and print in sections of the stage for the tanks as well as the domes that get printed using the wire arc additive manufacturing. These are then integrated together, and then the stage is taken to structural testing. This structural testing is also completed at Long Beach. This structural testing includes filling the tanks with water to do a pressure-proof test and also testing with structural loads. After testing and final integration, Stage 2 was transported to NASA Stennis, where we completed a full flight duration hot fire test. After structural testing and final integration of Stage 1 hot fire testing was actually done here at Launch Complex 16. Stage 1 hot fire used a special mount to simulate loads during flight. 6 ignitions of the Aeon 1 engines resulted in 185 seconds of hot fire on all 9 of those engines. Then we integrated Stage 2 and the nose cone after hot fire testing, and now we are here for our first launch. Let's take a look at our journey to launch.
As we approach T-minus 25 minutes, we're going to stand by for a situational briefing from the launch director, Clay Walker, in Mission Control. Let's listen in. We are just under T-minus 24 minutes, and we're currently waiting for an update from Mission Control. And I do have an update here from Mission Control. We did just get an updated tea time from the range of 1400 Eastern. Again, that's 1400 Eastern. That'll be reflected shortly on the tea clock. There you go. We are now 1 hour away from our launch. Our hold and extension of our T-clock is due to us wanting to get more time for propellant conditioning. We're going to stand by to hear more from Mission Control, but as of now, we are launching at 1400 Eastern. And you see the T-clock is no longer paused now. We are counting down. We are at now T minus 58 minutes and 18 seconds. For those just joining us, we are at T minus 49 minutes. As a reminder, we set back the T clock to allow us more time for propellant conditioning. In the meantime, why don't we talk about Stage 2 MDC?
Great idea. One of the approaches we take here at Relativity is to be focused on having a lot of hardware that we can test in order to reduce our risk getting into flight. One attempt that we tried to do that was paved out through successful testing was Stage 2 hot fire testing. This is where we took Stage 2 to NASA Stennis and we integrated the Aeon vacuum engine with a stub nozzle. For this test, we filled the tanks with our cryogenic propellant, and this is also where we were able to fire the engine and see interactions between the engine as well as the stage. What's really important about this type of testing is that it allows us to reduce risk. It allows us to test our propellant estimation algorithms. It also allows us to test how we pressurize our tanks. We got so much learnings from these tests, and why don't we take a look at that journey to Stage 2 hot fire testing.
My name is Zach Rubin. I'm the second stage RE. We're here. We have the flight engine on the flight stage, and we are going to do a full mission simulation starting with terminal count through Stage 1 burn and Stage 2 burn. Obviously, Stage 2 burn is going to be the main event, and if it all goes well, we'll accept it for flight.
5, 4, 3, 2, 1, 0. This was the first attempt at our actual mission duty for the flight vehicle. It was the first attempt. We went full duration on the first try. It was really cool to see all the teams finally come together. Avionics, flight software, ground software, prop, fluids, stage and ground systems. Really cool to be a part of.
As we continue to wait, can we get a brief update on the mission going on today?
Yes, so we are a little bit less than about 50 minutes until launch. We are still we took it back to be able to condition our propellant, so we're still doing that at the moment. But the range is green and the weather is looking great.
We are still moving forward, team. As we continue to wait, we just saw a video about Stage 2 mission duty cycle testing. We reached that full mission duty cycle duration for Stage 2. Similar to Stage 2, for Stage 1, we also completed stage hot fire testing. However, that was here at Launch Complex 16 instead of at NASA Stennis. We actually utilized our launch pad and adapted it to also have the capability to do Stage 1 hot fire testing. Let's take a look at this video.
Hello, I'm Pat Svatek. I'm the Cape Operations and Launch Site Director for Relativity here at Launch Complex 16.
Clay Walker, I'm the Director of Test Operations.
The objective for the test campaign for Stage 1 was to ensure that what we designed and built was going to be functional as intended.
A spin start is the least risky way to start the system and validate the timing for actual full combustion.
Specific points that we were looking to see in the spin start campaign was to make sure that we had the timing sequences correct.
It's pretty similar to any industry standard that you would expect. Very thorough and very impressive.
We chose to do our Stage 1 hot fire campaign at the actual launch site.
What we're hoping to look for is that the system responds appropriately. The engines feed the stage pressurization systems, and then the pressurization systems feed the propellant feed systems for the engine. They all have to be able to rely on each other, and that's what we're looking for.
It's all about testing the fully integrated system, all 9 engines on Stage 1 together to validate the individual stage is ready to go into the full-blown campaign for static fire launch.
Ultimately, what we look for in acceptance testing is, do we have enough data to confidently say that we're going to be able to hit our flight objectives? We got the system health verification that we're looking for. It's been almost 3 years working on this program, and to actually see the completed hardware standing on the pad, it's very exciting.
I'm very proud of the entire Relativity team. Quite frankly, it takes everyone across the company to be successful, and we had a bunch of folks across the company, from engineers, technicians, and support services across, to help us out and make sure that we were successful.
If you're just joining us, we are just under T-minus 33 minutes. We are progressing well towards our launch time of 1400 Eastern. If you missed the delay, the hour push was due to propellant conditioning. We wanted to get more time to continue that operation, and we're currently doing a great job. Everything is still green and a go for that launch time.
That is great to hear. I am so stoked to keep moving forward. As we continue to wait, maybe let's take a moment to recognize the technicians that helped us build the rocket that you see on the pad today. We wouldn't be where we are today without all of their hard work and effort to build this rocket. Let's take a look at this video.
Something that makes Relativity and all of its technicians unique is that we all come from very different backgrounds.
I was a freelance 3D animator. I also was working on motorcycles. I was working on guitar parts. So lots of hands-on actual manufacturing and fabrication. So this was really like a whirlwind of all the things that interest me.
Prior to joining Relativity, I was a teacher and a football coach. And I made sure that our kids were preparing for college and doing study halls, and they turned the tables on me. I had the passion to do it. It was something I wanted to do. It was something I wanted to make that career change and get into.
I was previously in the Navy for 5 years, worked on helicopters, built engines and rotary. And then that led me into the aerospace world, and there I built other rocket engines and pretty cool stuff, and that eventually led me here, which was very relatable to what I've done in the past. And it's pretty cool being part of a company in the earlier stages.
So I think my career really first started when I went to school at Cal Poly SLO. I went into my first manufacturing class, Machining 101, and the teacher in that class saw that I was really interested in using my hands to make things. And I really knew that that was my passion because I dived in deep with it.
At first, my favorite part was robots, lasers, and, you know, computer programs. So now I can say it's the people. I love the people here. Everyone, all the new hires, all the people that I met coming in, everyone is genuinely excited to be here.
One of the great things about here is attention to detail. We have to be meticulous about the things that we do because, you know, these little measurements are going to carry on to affect other things that are carry on to affect something else. The importance of it is never lost on me, and that's exciting.
Me as a technician and the experience that I've gotten throughout the years, I'm able to bring it here to Relativity. And working with the other engineers and the other technicians, we like to collaborate and bring those ideas together. And it's exciting to know that our input is worthy here, and so it can go far further, so it's pretty exciting.
I think the coolest part of my job is that right now I'm getting to help design the machine shop for our next headquarters. And so that's not just copying the machine shop that we have now, that's thinking 5-10 years into the future and thinking, what are we gonna need and how can we improve what we have now and how can we really spend the time planning this out. And so I have direct control over what that's gonna be like. And I think that's amazing.
you can see, we have placed another hold on the T clock at T minus 24 minutes. We do need additional time for propellant conditioning. We're going to stand by for additional updates, and I'll send that to you as soon as I have them. are currently holding the clock and taking it back once more. We just coordinated for a new T0 time with the range. Our new T0 time is now 14:40 Eastern. That is 2:40 p.m. Eastern. We're going to allow a little bit more time for propellant conditioning. As some of you may know, this is not at all unusual for a first launch. This is perfect for a first launch. This is perfectly expected since we want all systems to be as perfect as possible before we do this. If you're just joining us, we are now back at T minus 38 minutes. We did set back the clock and coordinated with the range for a new T0 time of 14:40 Eastern. That is 2:40 p.m. Eastern. We did add this time to allow us to continue our propellant conditioning. We'll continue to provide you updates as we get them. you're just joining us, we are currently at T-minus 23 minutes. If you recall, we did set the T-clock back a little bit in order to allow for propellant conditioning. You might also be able to see that the clouds are coming in. Our team is keeping a close eye on the weather right now just because we want the maximum visibility that we can get for this historic first launch. We'll keep you updated along the way. We're We're going to stand by for a situational briefing from the launch director, Clay Walker, in Mission Control. Let's listen in for the next few minutes. hearing now that we're expecting the go, no-go polls to occur in approximately 3 minutes. While we wait, let's talk about the nose cone that we have today.
So we don't have a customer payload on board, but we do have a memento inside of our nose cone. We have included our first ever 3D printed piece from our Stargate printer. And of course, it was a failed print since no one had ever done it before. As you see on your screen, that is our nose cone memento. That piece is 6.5 inches in diameter and weighs about 3 pounds. It is our first completed circular test article for which we used our first generation aluminum alloy. Since then, we've added a machined centerpiece with GLHF, good luck, have fun, and our mitosis logo to commemorate this maiden launch.
From our very first failed print 7 years ago, Relativity's team relentlessly overcame thousands of challenges against all odds to get to today, our first 3D printed rocket launch. Like the first print, Terran 1 is the first step of many towards making humanity a multi-planetary species. As a reminder, our primary objective for today is to gather as much data as possible to help develop our future vehicles, including Terran, our larger medium to heavy lift reusable launch vehicle. In just a few minutes, the launch director is going to poll the teams for launch, so let's listen in.
Go. FTS.
FTS go.
FTS go. RF.
RF go.
RF go. GNC.
GNC go.
GNC go. Flight software.
Flight software go.
Flight software go. Prop 1.
Prop 1 go.
Prop 1 go. Prop 2.
Prop 2 go.
Prop 2 go. Fluids 1.
Fluids 1 go.
Fluids 1 go. Fluids 2.
Fluids 2 go.
Fluids 2 go. Loads.
Loads go.
Loads go. Rock. Ranges go. OSM.
OSM is go.
OSM is go. RC. RC go. Vehicle.
Vehicle is go.
Vehicles go. CE.
CE's go.
C's go. LC.
LC go.
All parties have reported go for launch countdown. Once the T-clock begins, anyone can call for a hold at any time. If a hold is called prior to T-minus 70 seconds, the T-clock will continue to roll until T-minus 70 seconds, at which point a hold will be automatically initiated. A hold is not possible after T-minus 70 seconds, and any hold call after that time will result in a terminal count abort. Should a hold or manual abort be necessary, the person calling for a hold or abort should state clearly on comms, hold, 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 or abort, abort, abort. In the event that the OSM requires a hold, OSM will initiate the hold command on the OSM GUI and notify LD and the RC on the primary net.
LC-16 on Bravo, can we open stage 1 fuel bleeds, please?
Copy. Opening stage 1 fuel bleeds.
GCVC, please limit comms channels to Alpha, Bravo, Charlie, and countdown unless directed by the LC or LD.
Support room, this is vehicle on LV.
You just heard our launch director complete the go, no-go polling with our mission control team. All systems, as you heard, are currently healthy, so as of now, we're able to proceed with our scheduled launch time in about 12 minutes.
Throughout today's live stream, you've been hearing callouts for mission control. Let's take a moment to introduce you to our mission control team. Clay Walker, launch director. John Wiswall, launch conductor. James Harris, chief engineer. Elijah Escobedo and Zoe Dickert on vehicle controls. Brian Batters, ground control. Bill Stack, ground. Joy Mosdell, range control. There are a few notable members of leadership supporting today's launch who are also here at Launch Control. This includes our co-founder and CEO, Tim Ellis, our Chief Operating Officer, who leads product execution, Zach Dunn, Vice President of Test and Launch, Don Katterbeck, and Director of Cape Operations, Pat Svatek. These are among many, many others who are making today's launch happen. For those of you that are just tuning in, you can see Terran 1 on the pad. This rocket is 85% 3D printed by mass. It is 110 feet tall and 7.5 feet in diameter. Stage 1 has 9 Aeon 1 engines, and our second stage has an Aeon vacuum engine. These engines are also 3D printed using powder bed fusion. We're going to go ahead and take a moment to pause and stay tuned as we wait on the launch countdown.
We are getting extremely close here. Our countdown sequence will begin in T-minus 10 minutes, so just 30 seconds away.
T-minus 10 minutes, countdown sequence has started.
We're currently at T-minus 9 minutes and 40 seconds. In the upcoming minutes, you're going to hear several call-outs from Mission Control as we go through the final pre-launch procedural steps, including the priming of the igniters, final engine checkouts, transporter erector retraction, and getting that final go for launch. Again, we're now pressing the tanks to flight pressures, and we're currently proceeding with our scheduled launch time. We'll be looking for a call out in the next 30 seconds that stage 1 is transitioning to helium.
Stage 1 pneumatics have transitioned to helium.
There you go. That means we're pressurizing the propellant tanks to flight pressures.
Chill.
We'll be charging these stage 2 igniters to flight targets in just about 10 seconds.
We are now getting into the business end of today's countdown.
Stage 2 igniter to flight target.
Arwa, let's go ahead and walk through the launch timeline.
Yeah, sure. At T-minus 3 minutes, the transporter erector will retract just a few degrees to give the proper angle for umbilical separation. At this point, the vehicle will be on internal power. At T-minus 70 seconds, the vehicle will go into terminal count. This is again when the vehicle's internal flight computer takes control of the countdown. We then go into final flight termination checks and get FTS go from the launch conductor in coordination with the mission flight control officer and operation safety manager. At T-minus 6 seconds, we'll have ignition of those 9 beautiful 3D printed Aeon 1 engines, so you'll see the flames beneath the rocket at that point. And at T0, we will have liftoff. Shortly after that, at T plus 2 seconds, the strong back will throw back to assist in removing the umbilicals and clear the path for the vehicle to fly vertical. At T plus 12 seconds, we'll begin our pitch over program, and at T plus 80 seconds is that important milestone of max Q, or the point of maximum dynamic pressure. This is again where the structural loads on the vehicle are the highest, making it one of the more challenging phases of flight.
At approximately T plus 160 seconds, we'll have main engine cutoff, or MECO, where the stage 1 engines will shut off, followed shortly by stage separation and the Aeon vacuum engine igniting. Second stage will burn for a little under 5 minutes, and then at approximately T plus 463 seconds, we'll have second engine cutoff, or SECO. As a reminder, we do not have a fairing or any payload deployments for this first launch. With that, we'll go ahead and wait and stay tuned with Mission Control.
And once again, we are so honored to be hosting this launch with you all today. I'm Arwa Tizani-Kelly, Technical Program Manager for Test and Launch at Relativity Space.
And I'm Rachel Aniceto, Chief of Staff for the Vehicle Architecture and Technology team.
And we are now less than 5 minutes away from watching the world's first 3D printed rocket launch.
Stage 1 igniters priming in.
We're currently priming the igniters with gaseous oxygen and gaseous hydrogen. Our ignition system uses these propellants flowing across a glow plug.
Stage 2 is on internal power.
And you just saw the transporter erector cradle disengage.
The cradle's disengaged.
There we go. The cradle arm slowly started releasing stage 2 at the top there so that the strong back can retract, and we confirm that stage 2 is now on internal power.
Stage 1 is on internal power.
Stage 1 TVC checkout complete.
We just completed Stage 1 TVC checkouts. That means that we performed the final thrust vector control health checks on both stages before liftoff. We'll be doing Stage 2, or rather completing Stage 2, within the next 10 seconds.
Stage 2 TVC checkouts.
Next up, we'll be retracting the strong back, and then our range coordinator will ask the range for their status one last time.
Rock, report range status.
Range green.
And that was confirmation that the range is green for launch. We are almost a minute away.
Announcement on countdown net. This is the LD. We are holding at T-minus 70 seconds prior to terminal count to address issue.
All right, you heard Clay Walker, our launch director there. We are holding at T-minus 69 seconds to address an issue. We are, however, at the same time retracting our strong back. That black truss structure there is the strong back. It'll retract just a few degrees to prepare for umbilical separation. We'll stand by for further updates from Mission Control, and we'll update you on the hold. As a reminder of what our launch director said earlier, this is the last opportunity that our team can call a hold. So the team chose to take that option at T-minus 70 seconds and ensure everything is nominal before we go into our terminal count sequence. Again, what you're looking at in front of you is 85% 3D printed, and it is about to fly. Those white clouds you see coming out of the rocket are due to the venting of the chilled gas from the rocket into the humid Florida air out here. That's why the gas condenses into vapor and looks like clouds. I'm hearing that our T-clock will resume in about 1 minute.
Announcement on countdown. This is the LD. The T-clock will resume in approximately 20 seconds. Transitioning to terminal count.
As a reminder, from here on out, when the T-clock resumes, our countdown sequence will be automated and controlled by the internal flight computer. We are extending the hold just a little bit longer. We're going to stand by for further updates from Mission Control.
Announcement on countdown net. This is LD. We have had a terminal count abort, saving the vehicle and assessing recycle options.
You heard that announcement from our launch director. We're going to have an update momentarily as to what happened with our automated abort. If you're just joining us, we did have an automated abort at T-minus 70 seconds. The team is currently assessing if we're able to recycle since we are still within our launch window. So we'll provide that update as soon as we have confirmation from Mission Control. Once again, we had an automated abort at T-minus 70 seconds. Our launch director and our teams in mission control are currently assessing the recycle options that we have for today since we're currently still within our launch window. We're standing by to hear that update from Clay Walker. All right, I just received confirmation that we are going to recycle, and we have an updated T0 time of 15:55 Eastern. So again, that's 15:55 Eastern, approximately 45 minutes from now. We're gonna keep going. To provide an update on the cause of the previous automated abort, the stage 2 oxygen temperatures were out of limits, so that's why we had that abort at T minus 70 seconds. Now we're going to resolve this issue and continue on with our recycled and new T0 time of 15:55 Eastern. Quick update here that our updated launch time that's been confirmed with the range is at 15:45 Eastern. That is 3:45 p.m. Eastern. The T clock at the top of your screen is accurate and will keep you up to date as to when we are going to lift off. We are currently at T minus 23 minutes and 56 seconds. We're currently waiting for an update from Mission Control. Let's continue listening in and stand by.
Countdown net, this is the LD. All parties, we are scrubbing operations for the day. Thanks for playing.
All right, you just heard that update from Mission Control. We are unfortunately scrubbing today's operations. We're going to stand by for additional details from Clay Walker. just got word from the launch teams. We're scrubbing for today's launch temp due to A. Remove that and put in her first. As you saw, we unfortunately scrubbed for today. But while we obviously had high hopes for sending our Terran 1 off today, we're going to continue to take a measured approach so we can ultimately see this rocket off to max Q and beyond.
Once we have an update on the timing for our next launch attempt, we will share that via Twitter at Relativity Space. We hope you will join us again soon to see the world's first 3D printed rocket fly. I am Rachel Aniceto.
And I'm Arwa Tazani Kelly. Thank you, and see you next time.